Welcome back, focused learners. Today's explainer is diving into a massive, fundamental shift happening right now in the world of artificial intelligence. For the past couple of years, we've kind of looked at generative AI video as just this fascinating and, let's be honest, sometimes totally surreal creative Troy. But the data is actually telling a wildly different story. What we are witnessing here is the evolution of AI video generation into a serious, zero-shot reasoning engine. That means it can intuitively solve really complex problems that it was never explicitly trained for. We are looking at a system that doesn't just generate pretty pictures, but actually understands and manipulates the physical world.
To really grasp this evolution, here is our roadmap for today. First, the next AI paradigm shift. Then, meet VO3, the generalist. Third, thinking in frames, COF. Fourth, the hierarchy of capabilities. Fifth, scaling video like LLMs. And finally, a unified vision foundation.
All right, let's kick things off with Section 1, the next AI paradigm shift. So, to really get a handle on this, let's draw a stark contrast. We all saw how large language models completely disrupted natural language processing, right? Instead of having one bespoke, custom-built system for translation and a totally separate one for summarizing and another one just for coding, LLMs basically unified the whole shebang. A simple text prompt conditions the model to auto-regressively produce words. Well, guess what? Video models are doing the exact same thing to computer vision. Instead of juggling these fragmented, highly specific systems for tracking, edge detection, and segmentation, we just use a seed image and some text instructions to condition the model to produce frames. It's wild. Autoregressive video models are literally stepping in to replace highly specific, fragmented vision systems entirely.
Moving on to Section 2, meet VO3, the generalist.
To really understand what VO3 brings to the table, we need to look at the deliberately minimal evaluation framework they use to test it. The setup is remarkably straightforward. VO3 is prompted with nothing more than a seed image and a natural language instruction. From just that, it generates 8-second sequences at 720p resolution and 24 frames per second, all processed via Google Cloud Vertex AI. The researchers actually evaluated a staggering 18,384 generated videos. And what they did here was compare VO3 against state-of-the-art models, things like Nano Banana and SOM-V2. Now, it's absolutely awe-inspiring when you realize that those are highly tuned, dedicated image models, and VO3 is going toe-to-toe with them as a broad generalist. By stripping away all the complex scaffolding, this evaluation framework keeps the spotlight purely on VO3's raw generative capabilities.
Which brings us to Section 3, thinking in frames, or COF. If you follow text-based AI at all, you definitely know about chain of thought, where a model breaks down a logic problem step by step using text. Well, we can playfully contrast that with chain of frames, or COF. It's essentially the direct temporal analog for video. Instead of decomposing a reasoning problem into symbolic text steps, VO3 breaks the reasoning down into visual temporal increments. It quite literally thinks sequentially through video frames.
And what's absolutely fascinating here is how this totally reframes the whole idea of autoregression in video generation. When the model generates frame 1, and then frame 2, and then frame 3, it isn't just drawing a flipbook. Every single generated frame is actually a step in a complex reasoning process. As this quote perfectly notes, these intermediate frames act as latent reasoning traces. They essentially encode partial progress toward a solution. The visual frame itself has become the model's scratchpad.
Let's look at what this enables in Section 4, the hierarchy of capabilities.
So let's see how this actually builds across 4 progressive levels of emergent abilities. And keep in mind, these are skills the model essentially taught itself purely from temporal coherence. It's wild. Step 1 is perception, which involves low-level operators. Step 2 is modeling, which requires intuitive physics. Step 3 is manipulation, allowing for scene transformation. And Step 4 is full-on reasoning, utilizing temporal symbolic planning. Let's dig into each one of these.
Starting right at the base with Step 1, perception. When researchers measured edge detection accuracy using the OIS metric, which is basically a score of how perfectly the AI traces the true boundaries of an object, VO3 hit a 0.77. That is rapidly closing the gap with highly specialized state-of-the-art models that are sitting at 0.90. This tells us that perception tasks like edge detection, segmentation, and super resolution are emerging naturally. They are just byproducts of the model trying to keep a video temporally coherent. Amazingly, the source even notes that VO3's edge detection often beats the ground truth dataset annotations. That suggests it's actually finding a perceptual granularity beyond even what it was explicitly trained to see. Crazy, right?
And that brilliantly illustrates our second step, modeling.
Get this, VO3 was never explicitly programmed with the equations for Newtonian dynamics. It essentially skipped high school physics entirely. Yet, just to keep objects consistent from frame to frame, it went ahead and built its own implicit world model. It intuitively simulates Newtonian dynamics. We're talking gravity variation, material deformation, buoyancy, and even light refraction, all simulated accurately.
So the really crucial point when we get to step 3, manipulation, is that all of that perception and modeling allows the AI to actively edit scenes, because it understands the physics and the boundaries of objects, what researchers call latent disentanglement, which basically means it can mentally separate an object from its background. It allows the model to treat visual elements almost like physical tools. And this gives us incredible zero-shot capabilities for things like background removal, novel view synthesis, character reposing, and really complex style transfer.
Finally, we tackle step 4, the pinnacle, reasoning. We can actually see this in action with how VO3 solves mazes. It literally draws the path through a maze incrementally, frame by frame. It almost looks like an algorithm unfolding in real time. And just like with text LLMs, we see a massive difference in success rates based on compute time. If you give it just a single attempt, a pass at 1, success is naturally a bit lower. But when given 10 attempts and more inference time to really think about it, the success rate drastically improves. It is actively reasoning through visual constraints.
Okay, moving right along to section 5, scaling video like LLMs.
The massive leap in performance we've seen from VO2 to VO3 proves that these emergent capabilities are absolutely not a fluke. These massive gains popped up without a major architectural overhaul. They were strictly triggered by scale. Today, VO3 really mirrors the early trajectory of LLMs like GPT-3. Sure, it might currently underperform deeply specialized task-specific models in some narrow benchmarks, but it is demonstrating incredible adaptability and breadth. Plus, inference costs are declining super exponentially. What we're looking at is a predictable scaling law, and it's pointing directly to an eventual widespread economic feasibility where using generalist video models is just going to make way more financial sense than maintaining hundreds of bespoke vision systems.
And that leads us to our final section, section 6, a unified vision foundation.
We've seen throughout this explainer that the current computer vision ecosystem is, frankly, highly fragmented. But video, inherently, is the absolute perfect foundation to collapse all of that into a single, elegant, generalist architecture. Think about it. Temporal coherence naturally enforces physical reasoning. The frame-by-frame autoregression seamlessly enables that stepwise chain-of-frames reasoning we talked about. And its multimodality aligns perfectly with text and symbolic constructions. So, why does all of this matter for us? Because video models are now positioned to completely subsume segmentation, detection, physics simulation, and editing, all under one roof. The generative prior alone instantiates the whole spectrum of classical vision operators. It is a total game changer.
This progression from image-specific tools to these generalist video foundations marks a truly pivotal shift in the industry. We aren't just looking at video generators anymore, folks. We are looking at zero-shot learners and physical reasoners. The deficits we see today compared to specialized models, those are likely temporary. But their generality, that is a permanent, massive advantage. Which leaves us with one ultimate question to ponder. As computational costs continue to fall and capabilities inevitably scale, are video models about to completely redefine computer vision itself?